ask everybody to show their appreciation in a proper way, but we can hardly do that virtually. We're moving now into a panel discussion. Could I ask Bert to stop sharing his screen, please? And for my panelists to turn their videos on, if possible. And hopefully there will be 4 people turning their videos on shortly. Well, there's one, Yoshide. Ted, yeah. And who are the other panelists? Oh, Owen, there, fine, another one, and one more. There we go, Kenny in late night in Sydney. Thank you, Kenny, for that. I'm going to just read their biographies, first of all, so you know who we've got here. And then I'll simply ask each of the panel members to react to what Bert has said and make some comments on it. And then I'll try and share a panel discussion with these folk. Professor Ted Stathopoulos is professor at Concordia University in Montreal. His main area of research is in wind effects on buildings and their codification. He's published in around 500 referee journal papers or conference proceedings. He's a member of the ASCII 7 committee and the Canadian Code, a fellow of the Canadian Academy of Engineering, the Institute of Civil Engineers, and the American Society of Civil Engineers. He's also in the wind engineering field, the editor of the Journal of Wind Engineering and Industrial Aerodynamics. He holds the post of Distinguished Professor in Building Physics, Urban Physics and Wind Engineering in University of Eindhoven, from where he has received an honorary doctorate, as well as an honorary doctorate from the Aristotle University of Thessaloniki in Greece. So that's my first of the panelists. Dr. Owen Clifford is a chartered engineer and currently works as a senior lecturer in civil engineering in the National University of Ireland in Galway. He's the program director of the BSc Construction Management course at NUI and academic director of the CEIM program in the School of Engineering. He's a visiting research fellow at the Athlone Institute of Technology. And as Bert said earlier, his key research and educational interests lie in the areas of fluid dynamics, cycling aerodynamics, wastewater and water engineering, and the development of tools for sustainable technology. He's also collaborating with Bert on modeling the aerodynamics of Paralympic cyclists on tandems and hand cycles. Kenny Kwok, Professor Kwok, is Professor of Engineering at the University of Sydney. His research interests include wind engineering, structural dynamics, vibration control, human perception of motion, environmental fluid mechanics. His research focuses on fundamental aspects of building aerodynamics, wind structure, occupant interactions, and practical applications. He's published over 500 articles in journals, book chapters, invited and keynote papers, and conference papers. He's the recipient of the 2019 ASCII Jackie Cermak Medal, the 2019 IAE Davenport Medal, and a life member of the Australian Wind Engineering Society. Professor Yoshihide Taminaga is Professor of Architecture and Environmental Engineering at the Professor of Architecture and Urban Environment Division and Director of Wind Engineering and Fluids Research at the Niigata Research Institute in Japan. His area of expertise is numerical and experimental modeling of microscale wind flows and related processes in the urban environment, including cross-ventilated room airflow, pedestrian wind comfort, air pollution, dispersion, snowdrifts, and so on. He served as chair of the Wind Engineering Committee of the Architectural Institute of Japan, which instituted guidelines for practical applications of CFD to pedestrian wind around buildings. A very distinguished panel, ladies and gentlemen. Could I first ask, in no particular order, could I ask Ted Stathopoulos simply to give his immediate reaction to what Bert said?
Thank you very much, Chris, for your invitation. I'm very pleased and honored, actually, to be part of this international seminar, of this panel. I'd like to say good day or good night, depending on where everybody kind of is located at this moment. And first and foremost, of course, I would like to thank Bert for his always interesting, exciting, and entertaining, actually, lecture with plenty of questions, keeping the audience always alert. His topic on outdoor and indoor ventilation and dispersion associated with COVID-19 transmission is not only of critical, but also of vital importance in our days, as everybody knows. However, in my short commentary here, I would like to focus on the second line of the title of Bert's presentation, and that was sense, nonsense, and beyond. I found it very interesting. Bert said, research is done not to confirm common sense, but to quantify the results of this common sense. However, do we all agree on what common sense really is? Based on my experience, the best definition of common sense is sense that most people do not have. Perhaps the most important thing in this particular context is what we call sound engineering judgment. This, of course, comes with scientific knowledge, careful, good observations, and, of course, experience. My academic work on the codification of wind effects on buildings has convinced me about the importance, it's very significant importance of this sound engineering judgment when interpreting research results and trying actually to transfer them into the engineering practice, a business which is much more difficult than most people think that it is. Bert also talked about the unethical behavior on the side of the media, quoting the famous statement, I like that one, a study has not yet been peer-reviewed, so it has to be wrong. Beyond the obvious fallacy here, and the kind of joking character of this statement, which unfortunately is serious, can anybody say with certainty that if a study has indeed been peer-reviewed, it must be correct? Using my editorial hat this time, I can state that this is not the case, at least in a number of instances. I have heard of anecdotal evidence that peer reviews have been completed within 24 hours. I have also seen cases in which some reviewers express opinions, as Bert also said, without having even read the study. Please do not take me wrong at this moment. I'm not against peer review. In fact, peer review is the best system in the absence of a better one, but it is far from being perfect. Bert also talked about changing the minimum social or physical distance. Only very recently, I understood the difference between social and physical distance. Initially, I thought it was all physical distance. When objects are not stationary, and of course, this makes very good sense. However, his studies did not consider the influence of the wind. Again, it makes good sense to expect that depending on the wind speed and direction, this distance could or should be increased, since the particles may move with increased momentum under the influence of the wind. Finally, I would like to stress, and this is mainly for our junior researchers and graduate students, the importance of wind engineering applications in addressing societal problems, sometimes even of pandemic character, as Bert's lecture has demonstrated so clearly today. Thank you very much.
Thank you, Ted. I'm simply asking people in the order in which they appear on my screen, which is doubtless, no doubt not the order they appear in other pieces. So I'll go to Owen Clifford next and ask if he'd care to give a comment, give his comments.
Hi, everyone. And just to say thanks as well for inviting me here today. And thanks to Bert for a very interesting presentation as well. I'm going to perhaps maybe focus on just a couple of parts of this. And the first thing maybe is somewhat similar to what Ted mentioned with regard to common sense. And in fact, one of the things when your study came out at that time with regard to the aspect of distancing and exercise was I had used the COVID opportunity. For me, actually provided a good chance to get back racing, bike racing. I hadn't raced in a couple of years, but I was working from home and I was able to go back racing. And of course, I was thinking, what would be the impacts of going back racing in a peloton exactly around that time. And I did I suppose, a very non-scientific, I should say, survey among my colleagues who I would train with. And I was asking them the scenario, would they rather cycle side by side with someone out training or 2 meters behind someone, because 2 meters was the physical distance we were given. And most people who I trained with said, oh, 2 meters beside someone. They felt that side by side was more risky. And I suppose my point being that I think, you know, common sense, and maybe that's what Ted was referring to, is not necessarily the same for everyone, because I guess they felt they were in closer physical proximity when they were side by side to someone, therefore it must be more risky. However, that may not necessarily be the case. And I just found that aspect of the study interesting, and they also found it quite interesting. Now I know, of course, there are you know, limitations and wind conditions, etc. But I do think that, you know, people probably didn't have the realization around walking in or cycling in people's slipstreams that we might think that people should have. So that's one aspect I found very interesting. I think the second aspect, maybe if I could just go maybe a bit broader, and I think it links very well with, I guess, the issue of ventilation. And I suppose the public health issue in general is perhaps the need for a wider role for engineers in these types of discussions. It's not just in this area of COVID, but also, for example, in my own area of sanitation and wastewater treatment, whereby quite rightly, a lot of the discussion is led by public health experts, and that's absolutely fine. But in many cases, the types of interventions or mitigation measures that one might like to implement are ones that will be driven by engineers. And I think we do, I suppose, as engineers, we probably need to be more vocal as to, you know, our own expertise in these scenarios. And epidemiologists and virologists have, you know, huge amount of expertise, but obviously people in the area of aerodynamics and fluid dynamics have expertise that can be very useful. And when you talk about ventilation of buildings, etc., I noted in Ireland recently there was a discussion on a news program, and there were 3 medical professionals who were in the discussion panel talking about ventilation in buildings, but no engineer, for example, or no architect in this discussion. And I don't know, is that common internationally, but certainly I know in my own area of wastewater treatment, something similar applies, that engineers are not brought into these types of discussions, even though we are the ones who design, operate wastewater treatment plants and a lot of the infrastructure that protects the environment. And I guess I think that's it really is a key point that the talk today showed in terms of the study you've done on both, I suppose, the bus environment, but also in the gym environment or indoor environments in general, is that this is a pandemic that we haven't seen before, but there is no reason to think that we won't see this type of pandemic again. And therefore, I think the involvement of engineers to both on the technological side and also in helping the public understand the type of factors that might help them, I suppose, be more safe and also limit the impact of lockdowns and things like that are, I suppose, very relevant. So I think they were the 2 key issues. I will say that I know in April, just to finish off, myself and Bert, we had an email exchange as to whether the professional cycling season should open again. And it's funny because the quotes you mentioned from the professional cyclists are true. When you're in the middle of a cycling bunch, it happened to me this summer, you're covered with all sorts of stuff, shall we call it, from cyclists around you. And yet, I guess when you're in the middle of the bunch, you don't really think of the associated danger of it, you know, and it's only when you stand back from these scenarios that you think of these things. So that's what I would like to, I suppose my immediate reaction to talk will be along those lines.
Thank you very much indeed. And again, just following the order I have on my screen, can I ask Professor Yoshihide Tominaga to make his comments, please? You'll need to unmute.
Oh, I'm sorry.
That's fine.
Thank you very much for everyone to have me. And first of all, I would like to express my sincere applause and sympathy to Bert for his excellent work and courage. And I think that Bert's presentation includes the importance and difficulty of communication with non-expert people. I think so. On that topic, can I share my slide now?
Yes, you should be able. You should have the facility to share screen.
Yes. So. Okay.
Yeah, okay, that's coming.
Okay. Can you see
Right,
my slide?
we can see a PowerPoint now, yes, yes.
Okay. Okay. So personally, I have to say thank Bart. Because I introduced Bart's work about runners. So in my research website. So this article tripled the access number of visits to our research center website. Thanks again. And so in Japan, the importance of ventilation has been, roughly speaking, widely recognized since the early stage of the COVID-19 outbreaks. So this is the announcement from the government. So it includes the warning with poor ventilation. So, however, the nature of ventilations, including natural and mechanical one, is not very well understood by the general public. So the emergency discourse by the president of two academic society, SHASE and AIJ, are released, named the role of ventilation in the control of COVID-19 infection. So in particular, the quantitative expression of ventilation is difficult to understand by non-experts, and it is confusing in some cases. For example, people think 1 air change per hour refers to opening windows once an hour. Furthermore, the qualitative aspect of ventilation, for example, ventilation efficiency, is even more hard to realize and control, especially non-expert people. So this is a bit old experimental results as collaboration with BAT. So that we compare the two different configurations with different window locations. So this is a simple visualization of the cross-ventilated flow. So in this case, the case A shows the larger airflow rates in comparison with the configuration E. But the bottom figures at the movie is the very preliminary CFD with droplet transport with different sites by my colleague, Dr. Shirzadi. So you can see the more small droplet. The blue shows the small droplet. More remains in the configuration A, even if the configuration A has airflow rates. So this type of phenomena is very complicated. So the visualization technique based on CFD and experiment will be useful for understanding such complicated phenomena such as ventilation. But as Bart shows us, the attention should also be paid to the risk of visual representations. So sometimes blind acceptance or rejection, both are undesirable, is possibly caused. That's my comments. So thank you.
Thank you. Could you unshare screen then, please?
Okay.
And our last of the speakers is, of course, Kenny Kwok, Professor Kenny Kwok from Sydney. So good evening, Kenny.
It's actually good morning. I just need 10 minutes past 12 midnight, but it's fine. I think First of all, I want to congratulate Bert for an excellent presentation, never disappointing in his presentation. It's worthwhile staying up to listen to that, Bert. And one of the advantage and the disadvantage being the last to make comments on. And I was going to raise the issue with Professor Clifford, him being a professional cyclist. And I think what Bert had presented, or the work that he had done, more or less confirmed some of the risk, cyclists or professional cyclists in particular face when they are riding in close formations. And I had the opportunity this year to actually pay more attention to watching the Tour de France. And that there has been, I believe, a small handful of cases of infection during the race. I wonder what role the cyclists and the transmission was responsible for that. Now, interestingly, now that we know and actually confirmed the obvious, the common sense, is there any plan to come up with meaningful or realistic mitigation strategy to try to minimize that risk? I couldn't imagine that it is at all realistic to insist that cyclists wear a mask or respirator to cycle. Maybe that's a risk that professional cyclists has to take. Because my background is more on building aerodynamics and dispersion in more a building environment. Nevertheless, I find the work that was presented very interesting indeed. One of the question that I keep on thinking is that there doesn't appear to be any doubt that the aerosol, the role the aerosol play in the transmission of COVID or a virus of similar nature. Accepting the aerosol is of the order of about 5 micron or below, and viruses is of the order of 1/50th of that size, 0.1 micron. I think shortly after sometime in April or May, there has been suggestion that in addition to aerosol transmission, there's also suggestion that transmission by air may be a potential transmission source. Now, of course, if virus of that small magnitude, it can easily be totally suspended in air and potentially can be transported at a much larger distance. I just wonder whether that is something that is worthwhile investigating. Now, moving into more a urban setting, we have the opportunity well, in fact, I was actually in Hong Kong when the SARS outbreak happened in 2001. And when one is in a heavily built up urban environment, then the airflow among closely packed building with unusual features sometimes play a role. I'm just curious to find out or question whether the wind structure interaction may play a role in a heavily built up area. In fact, in May, maybe April this year in Hong Kong, there was a suspicion that the waste vent discharge at the roof of a building may actually cause a re-ingestion of virus impregnated air or aerosol into some unit in a high-rise building. And now the related to that, of course, is that in a heavily populated area, cross-unit transmission may also play a role. This may be area that in addition to more a pedestrian level or in other more confined spaces, the role that ventilation play or wind structure interaction, physical structure may play a role. That may actually be an area that is worthwhile investigating. But anyway, in finishing, I want to, as I said, thank you, Bert, for some excellent work. And I look forward to the opportunity to sit down and read those papers and really digest the content in more detail. Thank you.
Thank you. Thank you to all the panel members. What's going to happen now is I'm going to put some questions and try and moderate a discussion between the panelists and Bert, if that's possible, for perhaps 15 minutes, something like that. Then we've been receiving some questions from those who've registered, and I'll spend another 10 or 15 minutes putting those questions to the panel. So we're not going to get through them all, of course, naturally. Being chairman, I can thoroughly abuse my position, of course, in this regard and ask the questions that I'm most interested in. I'd like to begin with a sort of general societal question, I think, because we've been talking about ethics and the like. And I'll ask you, anyone who wants to respond, to simply put your hand up and wave at me so I can call you in. But we're in the midst of a pandemic. Everything is being done in very much of a rush. Can I ask, what sort of areas of research you think are the most significant that we should take forward when we have a bit of leisure to do it? So either Bert or the panelists, if anyone would like to say, but please wave your hand. Owen?
I guess, well, I suppose from an engineering point of view, I actually think the area of ventilation is extremely important, and maybe key to that is, I mean, there's two aspects to ventilation. It's firstly, I suppose, what are the best means of ventilation that would allow more crowded indoor environments to, I suppose, take place with, reasonable level of safety. But secondly, there's also a social, I suppose, a socioeconomic aspect or an equality aspect to this as well, as that as engineers, can we challenge ourselves that we do know this pandemic tends to impact people who are of a lower socioeconomic income levels, etc. That may be due to where they live, density of population, the types of buildings they live in, and how are we going to tackle that problem as well? Because when we talk about ventilation upgrades, one can imagine that is going to be, I suppose, more feasible in buildings that maybe like office buildings where you have higher income people working, gymnasiums, places like that, where I suppose people who maybe come from higher income levels tend to attend those types of venues. But what about the scenarios, for example, where you have densely populated buildings, things like that? Can we, I suppose, develop solutions that allow retrofit of those types of buildings? And I think the second area for me is I would like, it's maybe not a particular area of research, but it's, I suppose, a thought, and I think I mentioned before, it's that I feel that engineers, we need to be more involved in the discussion around some public health issues. I think when it comes to decisions around lockdowns or what types of buildings should be locked down, etc., that the decisions are made, at least in an Irish context anyway, I suppose I shouldn't speak for other countries, very much by public health experts, which is perfectly understandable. But in some cases, input from other practitioners, not just engineers, of course, but other practitioners are necessary. And I think, engineers, maybe we need to push it, or I suppose bring our own skills more to the fore in these areas. So I guess that's not an area of research, but I think it's something that perhaps, does need to be tackled.
Any other comments? Ted?
Yeah, well, I agree very, very much with the previous comments, but I would like also to stress the importance of dispersion of pollutants or of substances or viruses or whatever. I mean, we found out that it's so important these days. In traditional wind engineering, there have been a lot of studies relating, for instance, to potential reingestion of pollutants in buildings and other structures and so on. But we have never kind of, done it to the effect to find minimum distances and minimum distances of moving or not moving objects, and take the effect of wind into account, as I mentioned in my short commentary, because I think this is very important, and people do not pay any attention to that. But really, this is going to have an influence on these minimal distances that we're talking about these days, and how important this is going to be. So more research in there, I think it becomes now very clear to me that it's necessary to be done.
Any other comments? I want to move on, ask you perhaps more technical question here, a sort of portmanteau of questions, really. And Bert, you'd expect me to ask this one. It's all about validation. As I seem to have a reputation amongst some of my colleagues as a CFD skeptic, I can't think why. But clearly you can validate velocities because of measurements in the wind tunnel. How easy or not is it to validate concentration, fluctuating concentration measurements? And associated with that is, when you make these measurements in model scale or full scale, what sort of time scales are you working to on the measurements? Now, others might be able to answer that question as well, but it's primarily at you, Bert, I think.
Yeah, yeah, I think, well, it's difficult. And I think it's comparable to what we have outside in let's say, most of our wind engineering work when we're dealing with pollutant dispersion. It's pretty it's pretty feasible to validate based on mean velocities. It's more difficult to look at standard deviations of velocity fluctuations, and then it's even more difficult to look at concentrations. And sometimes in concentrations, when we find an agreement within a factor 2, we're already very happy. So I think that kind of indicates also the range of accuracy that we can handle with these aerosol situations. The additional complexity is that aerosol measurement equipment is also not that cheap. So we have been using some really low cost sensors, and there, of course, we can put plenty. Like in the fitness center, I think we had more than 100. But you also see that the accuracy there is sometimes not good enough to really get working with these data. So it also means for validation that usually you'll have just a few points by which to perform your validation, and that of course still complicates things even further. And then of course there's the deposition of aerosols, the evaporation that is happening, and the aerosol shifting from bins with larger diameter to smaller diameter. So all in all, it's a nice topic on which one can spend the rest of his or her life. Just doing the validation of this kind of stuff. And I would say that the CFD simulations in this field, there have been quite some in the past 2 decades, especially, and some very good ones as well. But let's say we're still really at the beginning of exploring and validating what would be needed.
Can I ask, Bert, because it's come up in a number of questions that the audience has asked, is what can you give a few details of the CFD in terms of what type of CFD, turbulence models and the like?
Then it can range from unsteady rent simulations, like what we performed in the simulations that we showed, to scale adapt simulations, large eddy simulations. But since you are then often applying Lagrangian particle tracking, that also means that your computational power or your computational cost will go up quite dramatically. So that's why in combination with large eddy simulation, which may be something that you would want to do, might not always be feasible. The good thing, however, is that while mainly in wind engineering we're dealing in terms of building dynamics with outdoor urban areas that can be quite large, and with also very large total grid counts, that when you're focusing on an indoor environment, often the number of cells can be much more limited. And the challenge there will be the position on walls and the interaction with the ventilation system. And ventilation systems with swirl diffusers, for example, that also causes quite some challenges. So and overall there is still a general belief in the HVAC community that RAN simulations are fairly well suitable for indoor environments. While we know for the outside, it's quite a different story.
Yeah, thank you. I put this question to all the panel now. What then is the current state of knowledge of how, not how ventilation moves in buildings, but how aerosols and droplets move in buildings? Is there much background there that people know of, or is this a new field as well? Good wave. Or have I?
Well, I think if from all of us, I think Kenny is maybe the one that has been doing in his team most simulations of all 6 of us. Because a while ago he visited, well, before the pandemic, in better times, he visited Eindhoven, and he gave actually a fantastic presentation also on the previous SARS epidemic. So maybe Kenny could give some insights here.
Oh, well, you put me on the spot, isn't it?
Sorry.
Yes, I think you well and truly put me on the spot. I have a confession to make. I started off as an experimentalist. I really was a non-believer in CFD, and but then you probably heard me say that before. Is that, well, if you can't beat them, join them, right? And therefore, I start looking at it. I think what I want to reinforce is that earlier there's one question asked, is that what about benchmarking?
Yeah.
I think anyone that has been involved in physical modeling will tell you pollution dispersion study in a reduced scale is probably one of the hardest things to do in the wind tunnel. And I still remember that I observed one of the early, my first example was more than 40 years ago, watching Bill Melbourne doing tests in the wind tunnel at Monash University. And I find it fascinating. And I also concur with Bert, your observation that if you get the result within a factor of 2, you're doing well. All right. With that sort of figure in mind, it really, really is a challenge to get those things right. Now, then my next confession is that the sort of work that we've been doing, as I said, is largely, the vast majority of them are basically wind structure interaction. And we've taken the easy route in the sense, and that's probably one of the reasons why I said that we treat the pollutant, whatever it may be, to be actually fully suspended in air. And we actually stay well clear of aerosol. Some of the more recent work that we try to do, in fact, is also aerosol based. And that is, of course, Legionnaires Outbreak. Now, we have that on a fairly regular basis. And the source is well defined, is from air exchanger, the cooling tower. Now, if you ask me that question, as I said, I really do not have a quick answer to it, because modeling it in physical scale, we just couldn't do it. The closest we are looking at it is probably not aerosol. We actually are looking at reverse, is look at particulate, how they grow in size instead of what was mentioned earlier, is the aerosol. One of the major challenges is that they actually decrease in size once it's exposed in the atmosphere. And I actually will skip and actually let Bert answer the question. But I certainly believe that modeling aerosol, CFD has a very, very important role to play, because it can model some of the physical changes that in a physical modeling sense is extremely hard, if not impossible to do.
Thank you.
Pass the ball.
Thank you, Kenny. I want to move on now to actually, I was going to put individual questions from the audience to you, but they seem to be coming through in sort of themes, many of which we've actually talked about. One theme that seems to be coming up, and again, this I have to say is my interest, is the safety of transport and how COVID and aerosol moves around in transport. So I would ask colleagues if, and very much is known about that, and if Bert can say a little bit more about his bus work, it will make one or two of the questioners very happy. But is there very much out there? Because some say, you know, you shouldn't travel on public transport. Others say it's absolutely safe. Can I say that?
I think we've measured in 2 buses so far, and yeah, also these the ventilation rates certainly in the more modern buses are really very high. So talking about air change rates that Professor Tominaga also referred to in a funny way that it could be misunderstood by the public, is yeah, you're talking about air change rates of 15, 20 times per hour, which comes already close to what we have in airplanes. So that could suggest that the aerosol route might not be the first concern there. Nevertheless, yeah, not every spot in train, for example, or in a bus is equally well ventilated. We talk about these air changes per hour, but that's just a very rough ballpark number. You could have locations which are hot spots. Yeah, but I think, at least from the communication that I've received from the Dutch and the Belgian government, the reason why they, and I'm not saying that they make the right decision, but the main reasons why they have advise people to avoid public transport is the overcrowded buses and overcrowded trains, and actually the inability to keep this physical distance, which is interesting, by the way, because airplane travel has resumed, and I've heard that many planes are still fully packed. So there, apparently, we don't care that much about physical distance, but yeah, in buses and trains, it appears to be much more of a concern, interestingly.
I would make the comment, of course, that not all buses and trains have very modern air conditioning. The life of trains certainly is 20 or 30 years. Mm-hmm. So we're very often dealing with really rather old technology there. And so any guidelines that can be developed as to you know, what are acceptable air change rates and that sort of thing would be useful, I think. Any other comments on transport and COVID from anyone? No?
Oh, Chris,
yeah.
Can I make a comment?
Yeah, Mike, sure.
Because you know, I live in Sydney, and you know, fortunately, we don't have, you know, major outbreak per se. But very early on, I think public transport, the government had instigated a social distancing policy in public transport as well. And I have actually used public transport to go to work. Don't ask me why, but I did. I traveled by buses and train occasionally. And what they did was that on trains and buses, they actually put a sticker on designated seats that they expect people to sit on seating that actually have a sticker on, in order to maintain social distancing. Yeah. Now, we also have a tracing system in place. When they discover a sort of infected cases, if it has been on a bus or on a train, they will actually make an announcement and say that if you have traveled and during that time, you know, self-isolate, etc., etc. And they also advise, they never insist, you know, it's not a law that you have to wear a mask on the public transport. But if you ask me personally, I stick to those rules. But, and I also try to pick a non-peak hour to use public transport. and just as a precaution. But also observe that, occasionally people, certainly not many people actually wear masks when they go on buses and train. Now, interestingly, there hasn't been a case that I can remember in the last, 7 months or so, when this system has been in place, that has been a active tracing need to be done on train. There has been the odd cases on buses. Now, that may have something to do with the fact that those mode of transport actually have a above average or above standard rate of ventilation, as I believe the Bert actually mentioned earlier. Well, that's my 2 bobs worth.
Yeah. Okay. Thank you, Ted.
Yeah, just a few more points here, because I think they're very, very relevant to what we're discussing here. And that's where the issue of physical distance comes into account. So when you have a crowded bus, obviously this is to be avoided if possible. If the distances can be kept, I think that would be, relatively speaking, safe. However, in a lot of places, including Montreal now, the mask is absolutely compulsory. Okay, people are fined if they don't have a mask when they take the bus, because they cannot really take into account this distance. And that gives me an opportunity also to say something about the difference between physical distance and social distance. Okay, I was always intrigued by that, because a physical distance is something that everybody can understand. But there is a reason behind that, and this is that if you travel with a friend or with somebody that say that you have some social connection, and you start talking and discussing and laughing and so on, then of course chances are much higher that the virus is going to be transmitted. And that's why we kind of see a difference between physical distance and social distance. Now, assuming that people, they go on the bus, I mean, they're alone sort of thing, they don't travel with others, then of course things are a little bit much better. And with a mask there, well, things become, of course, a little bit more conservative. That's all.
Thank you. I'm going to draw the discussion as such to a close. We've had a set of comments from Professor Letchford, which is a sort of essay in itself, which I'm going to read to you. I don't know whether Chris would actually like to reveal himself by video as responsible for what I'm about to read. Is Chris there still? No, I can't see him. Maybe.
Yes, I'm here, Chris.
Oh, I see. Can you video yourself so we can see you, Chris?
I can try.
Yeah, okay. But I'll just read anyway. I'm not going to take discussion on this. I'm going to say this is where we end.
Can I just preface it with, it was a response to Owen's comment about engineers needing to be much more proactive in the real world. So take it away.
The ability to turn obstacles into opportunities to problem solve is described as your adversity quotient, AQ. Engineers need plenty of AQ. Engineers work in teams, large and small, to address problems of multiple sizes. For successful teams, the members must be capable of recognizing their own and other emotions and act on them effectively. This is typically known as emotional intelligence and measured by the emotional quotient, EQ. Engineers need plenty of EQ. Engineers need the ability to grasp multiple abstractions in solving problems as they simplify reality to an analyzable model. This has typically been measured by the intelligence quotient, IQ. Engineers need plenty of IQ. Engineers must achieve outcomes. They are practitioners, not theorists. An ability to achieve successful outcomes in the face of adversity through intelligence and harnessing emotions could be measured by an outcomes quotient, OQ. Engineers need plenty of OQ. Finally, engineers recognize that everything they design or construct has uncertainty, and quantifying the risk that is involved is crucial for efficient, sustainable, and economic solutions. To quantify uncertainty, we need engineers that understand uncertainty, and a measure of this understanding of uncertainty could be defined as an uncertainty quotient, UQ. Engineers need plenty of UQ. And that's Chris's comments. The one that struck me most, to be honest, and has become time and time again, is the need to be able to talk about uncertainty and to communicate uncertainty to the population, because that seems to be sadly lacking in the current pandemic of how people understand uncertainty and statistics. But I'm not going to take that any further at all now. I would say that we have reached where we need to stop. There are all sorts of other questions that could be asked, but I'm not going to. Now, I simply want to say thank you to Bert as a speaker. Thank you to the panel members. It's been very much appreciated. Thank you to Grace for hopefully doing the recordings, doing the questions. Thank you to her. Thank you all very much indeed. The recordings of the sessions should be online sometime within the next 24 hours, and I will send round an email to all registrants giving details of where you might find them. The next seminar will be on December the 3rd. It will have quite a different theme. It will be by Professor Ahsan Karim, the chairman of the International Association of Wind Engineering, looking at effectively wind engineering on structures, trying to draw lessons from the past as well as from the present. So thank you all very much indeed, ladies and gentlemen, and I hope you have a good rest of the day. I hope you have a nice night's sleep. And again, thank you.